I'm going to definitely change topic with respect to what we've seen so far. And I'm going to talk about early galaxy growth, and in particular about what is the role of agent feedback essentially in shaping the such growth of massive galaxies at high redshift. And to do so, I will mostly present results from this recent work, which we've been doing, especially together with Chiara Feruglio and Roberta Tripodi here in Trieste. And I would like to just start with a quick introduction to explain why we do care about agent feedback at high redshift. So what we know from the local universe is essentially the existence of tight scaling relations between properties of the black hole, such as the black hole mass, and properties of the galaxy, such as, for example, you see here the galaxy mass. And essentially, this is telling us that despite the very different spatial scales in place, essentially, some way the black hole has to know about the galaxy growth and vice versa. So this is called the sort of feedback cycle. And the basic idea is that when a quasar, a galaxy hosting a black hole approaches such a local relation, essentially the black hole drives winds, which are able to inject large amounts of energy, momentum into the black hole surroundings themselves and into the galaxy medium. And this process may influence black hole growth, but also galaxy growth in a self-regulating way. And the result being these nice scaling relations. But if we look at the high redshift, things are different. You have the local relation here, and if you put high redshift quasars on this plane, you see that they lay up here, which means that the billion solar masses black holes powering quasars, redshift 6, are about 10 times more massive with respect to their galaxies compared to the local relation. So essentially, this is telling us that this black hole had to grow more rapidly than their host galaxy during the first giga-year of the universe. And this is something that is not unexpected. Essentially, most models of early black hole growth and galaxy formation predict that at very high redshift, you have a rapid black hole growth. And then at certain point, let's say redshift about 6, 7, this growth has to significantly slow down, essentially due to agent feedback itself. However, despite predicted by simulations, from an observational point of view, it is extremely difficult to validate such a scenario. Agent feedback is also important to regulate the growth of the galaxy, and essentially it is invoked by, again, models of galaxy formation to prevent massive galaxies from overgrowing. Essentially, we need to keep the star formation efficiency low in massive systems, and the fact that we observe massive, essentially quiescent galaxies, even at high redshift, redshift 3, 5, they are continuously detected by JWST these days. So this is telling us that a feedback mechanism able to suppress star formation in the galaxy had to be present already at very early epochs, okay? So the first attempts to look for these black hole winds and to characterize their impact on high redshift galaxies comes from the millimeter band. You have here an example of this ionized carbon emission line observed with the ALMA. And the basic idea essentially is to look for high emission from high velocity gas. We are talking about gas moving at about 1,000 kilometers per second, which is not which cannot be associated with the bounded motion in the galaxy, but is indeed tracing this outflowing gas. And essentially, such winds are removing the fuel for star formation. This is the basic idea. But despite tens, if not hundreds of quasars, which with this kind of observations available today, these kind of detections of high velocity emission are quite limited. A few objects. So you have an example here. This comes from a stacking analysis of almost 50 sources. This is a recent example we found thanks to deep dedicated observations. But again, even the evidence that these winds are there is pretty limited to date. And the situation is even worse if we go to redshift above 7. You see here, again, deep millimeter observations with NOEMA targeting, again, the cold gas in quasar host galaxies. And essentially, these are the highest redshift detection of cold gas that we have so far. But you see, there is no detection of high velocity emission in this system. So essentially, we know nothing about outflows. However, I just wanted to mention that this kind of observation in general can bring a lot of information about, for example, quantifying the global abundance of molecular gas at such early epochs. Okay. So as cold gas seems to be like a not so efficient tracers of winds at high redshift, one may try a different approach, which consists essentially in looking for these broad absorption features in the rest frame UV spectra of quasar, because present-day instruments, as the X-shooter, for example, easily allow us to do this kind of detection even at the highest redshift. And these broad absorption features are tracing winds that at moderate redshift are observed in 10–20% of the quasars and have typical velocities of the order, again, of several thousand of kilometers per second. And these winds are expected to arise very close to the accretion disk, so very close to the black hole, but the absorption can occur farther away on up to kiloparsec scale. So these winds can have a feedback impact both on the black hole itself and on the host galaxy. Also because in those few cases in which we can measure the energetics of these winds, we find them to be very powerful and essentially consistent with our expectation for an efficient feedback mechanism. Using essentially the very deep X-shooter observations with an X-shooter large program carried out by Valentina Dodorico here in Trieste, we were able to push the search for these absorption winds up to high redshift, up to redshift above 6. And this has allowed us to assess essentially the redshift evolution of the wind properties as a function of redshift, okay? So the main result, you see it here. I was telling you before the typical values that we have in the intermediate redshift universe is about 20%, while at redshift 6, we found that essentially half of the quasar population shows these kind of winds. So we have about a factor of 2.5 difference. These winds seem to be extremely common at high redshift. And well, by building up a large control samples of about 2,000 quasars, opportunely matched and everything, we were able to rule out that this kind of difference was due to differences in terms of quasar properties, such as luminosity, black hole accretion rate. This is not the case. This is a genuine redshift evolution. And another interesting thing that we found is that these winds at high redshift seems to be extremely, they have extremely high velocities. You see up here, you have the velocity of the wind, again, as a function of redshift. And at redshift 6, we commonly observe the winds moving at 30,000 kilometers per second, which again is something that is extremely rare in the closer universe. So I'm going to skip this. So because there is, of course, there are many different reasons for why these may occur, but I want to focus on the fact that as the global energy injection of these winds, let's say by the quasar population at high redshift, is proportional to the fraction of quasars showing wind and to the third power of the wind velocity. This is telling us that we are having a huge injection of energy by the quasar population redshift about 6, which is about 20 times more than what we usually observed at later epochs. So this result is pointing towards a strong black hole feedback, likely affecting black hole growth, essentially shutting down the early, very rapid black hole growth that was necessary to build up these billion solar masses black hole that we have in these quasars. So moving back to the picture that I was showing you at the beginning, essentially, the idea is that at very high redshift, so in the left plot here, we have that quasars move essentially vertically in this plot. So the black hole grows much more rapidly than the galaxy, while at redshift about 6, we start having feedback. So it is possible that these sources might start approaching the local relation because the the black hole grows, shuts down, while the galaxy keeps growing. A key ingredient to assess in which kind of scenarios we are is essentially measuring an accurate growth rate of the host galaxy. Because so far I told you about the black hole, but the question is what happens to the galaxy? Because for example, if the wind is so powerful that it shuts down the star formation in the host, then the points stay there very far from the relation. So our knowledge of essentially the star formation rate in redshift 6 galaxies suffer from observational limitations. So from the fact that we are not able to accurately measure the infrared luminosities in such high redshift systems. And typically we have uncertainties on such quantities. Essentially, the final uncertainty on the star formation rate is of the order of 1 order of magnitude or more, because essentially current millimeter facilities allow us to probe the Rayleigh genes, the Rayleigh gene tail of the dust emission, but not the peak. So we are not able to measure the dust temperature, resulting in such large uncertainties. So we are currently doing a lot of work and trying to gather high frequency observations, essentially with ALMA in band 9. You see this point up here, which falls exactly on the peak of the dust continuum emission. And this implies that we are finally able to measure star formation rates at redshift 6 with uncertainties of the order of 10% or so. So we are really changing the regime. We may start saying something about the build-up rate of the galaxy. And this is another version, but it's again the same plot. So you have the black hole mass in the y-axis, the galaxy mass in the x-axis. This is the local relation. And in a couple of cases so far, we were able to accurately measure this arrow here, which indicates whether these quasars are approaching or not the relation. In one case, this is not happening. So the black hole keeps growing faster than the host galaxy. But in this other case, in which we know that there are winds, the arrow starts pointing towards the relation. So an intriguing idea is that at redshift 6, we might start witnessing the build-up of these nice relations between black hole and the galaxy properties. So I'll stop here and thank you for the attention.